Good day.
Yes.
Yes.
Yes, we can.
Good. So, on the previous lecture, we obtained this Friedman-Robertson, Friedman-Lemaitre-Robertson-Walker metric. And now today, we also spoke a little bit about energy stress tensor, for which describes the matter. So now our goal to find the cosmological equation, called cosmological equation, or it's called Lemaitre. That is a French name, Lemaitre. Okay. Equations. I will write parentheses. It's not the point to tell of universe, because when we speak about here Friedman-Lemaitre equation, it's already understandable. This is equation for the which allow us to obtain the evolution of the universe. So and to find the answer on the equation, what it was in the past and what it will be in the future, which is maybe for our time. So which is important not only for general things, but also, as we will see, it's also important as sometimes as a key or the additional possibility to choose the right theory of everything like this, joint interaction, which is a dream of all physicists. So, okay, to do this, we need to solve the Einstein equation for the Friedman-Robertson-Walker-Lemaitre metric. By the way, Lemaitre, there is, usually some stories about Friedman. I already said you the story. Lemaitre also has some, and I said you maybe already some times ago that he was a priest, so, and religion person, yes, priest. So, and he wrote the paper even before the Hubble, who found this linear dependence between distance to the galaxy and velocity, this linear dependence. Lemaitre found the solution before this, and he understood that to satisfy this cosmological principle, the universe should be dynamical object, and also as a result, it should be linear dependence between velocity and distance to the object. But when he wrote this paper and sent it to, as I remember correctly, to monthly notices, so the referee said, sometimes it happens, the referee said, come on, it's something strange. It's better not to tell about this. And Lemaitre erased this sentence about linear dependence. I say about V equal H multiplying R. And he cleaned it. Finally, a paper was published, and a few years later, Hubble discovered really this law, which for a long time, because this dependence called as a Hubble law. it suggested that maybe Hubble had some presentation talk of Lemaitre, because Lemaitre made some talk on some meeting, and Hubble already was ready for this point to find this law. Of course, he didn't quote Lemaitre because this sentence was raised in paper. And this in this story, very interesting story. Sometimes, you know, for the scientist, for example, don't give up, and sometimes it's happened why you are a little bit in front, and you discovered something new, and some referees say, it's not possible. So in any case, finally Lemaitre became the president of Vatican Academy of Science. So a very powerful person in Vatican. And later, like I don't remember, 7, maybe 6 years ago, it was scientists, astrophysicists, astronomers come back to this problem in sense that to satisfy these correct points that to remember Lemaitre and his discovery, which was by chance disappeared. And the International Astronomical Union voted to recall the Hubble law and call from this time as a Hubble-Lemaitre law, or Lemaitre-Hubble, I don't remember completely. So it was even joke to recall Hubble telescope, which you know very well, space telescope, to recall the Lemaitre Hubble telescope. So this is a story about Lemaitre, just you know to feel that it's not just letters, but or word, but this is was a interesting person, this interesting story about this equation of cosmology. Okay, now let's let's start. And so we finished on on energy stress tensor, and so this is important. We can put it in frame. And so we need to put this metric, Friedmann-Lemaitre. So I will this metric in Einstein equation. It's better to use Einstein equation in form. So you can write to find. Sorry, you can write to find the equation, cosmological equation, Friedmann-Lemaitre equation. We need to solve Einstein equation. For me, it will be convenient to solve it in the form like this. So in the left part, I leave only Ricci tensor, because you remember we have an Einstein equation 2 form. And on the right side, it will be 8pg divide c force t I k minus delta I k t scalar. Okay. So so about the right part. So on the left part we have geometry, and we need to put in this. This is Einstein equation, and to find this Friedmann-Lemaitre equation, we need to solve this Einstein equation, which, as we understand, in general case, since k from 0 to 3, it will be in component in general Einstein equation 4 on the 4, 16. So it looks like, mama, it's incredible to, you know, to analyze everything. But due to symmetry and due to cosmological principle, we will see that really we'll have only two differential equation. So in this equation, we need to put Friedman, Lemaitre, Robertson, Walker metric. And this is we remember a metric for which satisfy cosmological principle. So we all time need to keep, because when we finally obtain something, we need all time to remind which suggestion we put before. In sense that if we will meet in observation something strange, which we can't explain in framework of our theory, we can understand this is due to the fact that we put some suggestion maybe also wrong. So for this, we use cosmological principle that universe is homogeneous and isotropical on the big scale, more than 100 megaparsec. And so this is this for now, which we really can see from observational data. So this suggestion, this is not just suggestion, but it's satisfied to observations. But let's see what it will be in future. And also we need to put the matter on this right side. So we discussed that we also take into account even for energy stress tensor that it should be satisfy also this cosmological principle homogeneous and isotropical universe distribution of the matter. We discovered that this brings us to the point that velocity of the object should be zero. So the space expand or stretch. But the motion in global scales we don't have. So it's like a static in the space, but we will speak about evolution of itself, of the space itself. So, and this is exactly because we understand that we need to satisfy cosmological principle. As a result, we have this expression for the energy stress tensor, and we already should be happy because we can see that we have only diagonal elements due to the fact that the velocity is zero. And it's already better because our equation, we in advance can be sure that we will not have many equations. And so we found T00, T11. We also need to find, I will write here, it will be useful for me. So I will write here again, Tik equal P plus epsilon. Ik minus delta Ik multiply on P. So, and T00, we obtain it will be what, epsilon, okay. And so in my lecture, let's agree that if index equal from 0, we come from 0 to 3 together, space and time indexes, we put the Latin letters. But as soon as we consider Greek letter, it means, for example, alpha, it means that we speak about only space coordinate and only space, only component which are related with the space part. So, and I can write that T alpha, I look here, this we found, and this corresponds to this 3 equal minus P. Okay, if I will write the swapping part of the energy stress tensor, when this is Ti, so I need to consider the sum of all diagonal elements. It will be epsilon minus 3p. In this case, the right side of Einstein equation, this one, we can have we will have that T00 minus I even write delta 00, which is unity, multiply on T, and T00, this is epsilon minus sorry, this should be 1.5. Okay, so please correct. This 1.5, as we remember, come to us from a differential Bianchi identity, minus, and here should be 1.5, minus 1.5, epsilon minus, sorry, I write something stupid. No, right, minus 3p. If we calculate, this is epsilon minus plus 3p divided on 2, which is 1.5 epsilon plus 3p. And we also need to write to find alpha minus delta alpha on T. I mean, for it's not a good writing because it looks like it's better to write like this. Because it looks like a swapping. So I write alpha, beta, alpha, beta. So I mean that to find the expression, so it's understandable that we will have only the situation when alpha equal beta, because diagonal element will disappear. The only diagonal element will survive. So what we will have, this is minus T alpha beta, this is minus P, minus 1 divided on 2. Delta alpha beta will survive only when alpha equal beta and this equal unity. And here we need to put again epsilon minus 3p. So minus p minus epsilon divided on 2.
Why we have here only 1p but not 3p? No, here is summation or not?
In this place?
Yes.
No, this is not summation. It means that we want to obtain this expression. For example, T11 plus, minus 1.5 delta 1,
Okay.
T2 for 2 indexes. So this you need to explain in your conspect for yourself. So it's, of course, maybe, I just can consider only the right side, why it looks like this. So, but, okay. Okay, so plus plus 3p divided on 2. And finally, we obtain half epsilon, and here it will be plus p divided on 2. Okay, so it will be 1/2 p minus epsilon. So it means that if we will write non-zero component of Einstein equation, zero, of course, also can be. No, doesn't matter. We will put everything. So this Einstein equation, which we need to solve, we already know the right side of the Einstein equation. It means that on the left side, it will be R alpha, from the space component 0, 0 equal 8pg divided c. So divide on 2. I will put here 4. And here epsilon plus 3p. And for the space part of Einstein equation, we have R alpha beta equal again 4pg divided c 4. And here we put p minus epsilon. So this is Einstein equation, writing a component for their energy stress tensor, which describes the matter in the universe, the distribution. What exactly we'll consider which matter, we will discuss it later. So, and here we need to write that alpha beta from 1 to 3. Okay, this is time component, and this is space component. Einstein equation. So, and we need this business to calculate Ricci tensor, which we have on the left side, and which is exactly responsible for this for the curve of space, curvature of space, time, in general case. For us now, this is curvature of the space. So in any case, in time, for time equation, we also need to obtain corresponding equation. And to calculate the Ricci tensor, we need to use the metric which we obtain. So this metric, Friedman-Robertson-Lemaitre metric. This one. Okay. So I will write it here. S square equals c square dt square minus dr square 1 minus k r square a square minus r square sinus square theta dphi square plus. See, Enrique, I have my lecture now. All time I. Just a second. Time I am without lunch with my colleague. Okay, sinus theta dphi and plus the theta square. Okay, So we also can remember that if we will look on the dimension, we understand that this is dimension of r square, this one, 2. R, this is dimension of the length. And of course, if we look on this summand, we need to remember that in principle, we need to put here some R0 square, which is some dimension scale. So for example, the radius of the curvature of the universe like this. But again, we decided to put it unity, and just remember that if we will jump to take into account the dimension of the equation, we need to remember about this. Again, K, this is signum of scalar curvature, for example, and equal plus, minus 1 or 0. So 3 cases, and we also understand it because this is again correspond to cosmological principle. Yes, and okay, and the A, this is function of time, and this is exactly the scale factor. I will remind scale factor, which tell us how much the space change, stretch due to corresponding to equation of gravity. So this scale factor exactly, and the idea in final equation which we need to obtain is exactly to obtain the law for the scale factor. It will tell us about dynamic of universe. Okay, now we will make some trick because it's much more convenient to use to go and to use dimensionless radius, which are, we just will consider, and we will it just how to better to say reconstruction, rescaling. So R divide on A. Okay, again R0. Why we say dimensionless radius? So because R0, which again we remember this is unity. So and to rewrite Friedman Lemaitre, Robertson-Walker metric like this. So ds square equal c square dt square minus, and look, if I will do this, so I will rescale on this value, it just for convenient. So I will have, I need to divide and multiply this value. So I will have a square, which is function on t, okay, multiply on dr square, divide 1 minus k r square, and since I took out a outside of the brackets, parentheses is in Italian, brackets in English, already mix languages. So plus, I put here plus r square sinus square theta d phi square plus d theta square. Okay. So this is Friedman, Lemaitre, Robertson, Walker metric in this form. And so what we need to do the procedure to find corresponding Christoffel symbols and Riemann tensor together with Ricci tensor to find the left part of this equation. By the way, when we speak about Einstein equation, we will speak a little bit later about cosmological term and dark matter. Sometimes, so I also would like to remark that this is Einstein equation without lambda constant, lambda term, which is responsible now and very important for now as because it's described dark energy, but later we will consider this too. So, okay. So just clarify now what is the coordinates. X0, this is CT, X1, this is R, X2. I will find now only one component of Einstein equation. The space component, it will be exactly home task for you. So now you will look how I am doing it for time component and to repeat it for another one. For the space, it will be a little bit complicated, but I don't want to spend time as a lecture. So and phi. Okay. So what is a metric tensor? Metric tensor, for this metric, we write that G0, 0, we will have only diagonal element. This is 1. G1, 1 equal minus a square divide on 1 minus k r square. J2, 2 equal minus what is in front of phi, what is in front of theta, it will be minus a square r square, and J3, 3 equal minus a square r square sinus square theta. So we have everything to start. Just a second, I need to answer. Okay. So for Christoffel symbols, And now I will show you some procedure, because we can quickly discover that we can find, we can prove that if we have Christoffel symbols with indexes which are repeating kk, for example, here, it will be 1 divide. I will find. So I'm sure that it should be simple. I will remind that I k L, for example. Okay, so this is 1 divide on GIM divide on GMK L plus GML K minus GKLM. So this is expression which we found. Now let's consider if we have the same index k here, k here, k here, and k here. So in this case, we understand that we will have only the situation when it will survive. I'll write like this: when m equal e. Why? Because only diagonal element of the metric tensor are not 0, others are 0. So why we need to put m equal e? So we need to put here e, and e. Let's write what we will have finally. So we have 1 divide on GII, GIK, k minus GIKK minus plus GKK I. So, and in this case, I don't equal k. It means that this will be 0, this will be 0, because this is diagonal element, and we will have only, and I will put it here, 1 divide on 2 minus GII, GKK I. So this is more simple expression which we immediately can use to obtain component of Christoffel symbols for this metric. For example, we have I would like to find gamma, which I will need 1, 1, 0. So I just will use this expression because the index is repeated, and I need to put 1 divide on 2 G0, 0, D G1, 1 divide on D X and E equals 0. Okay. So 1 divide on 2. Here we write covariant component of metric tensor. So, but we need to put here contravariant component, and it means that we this is 1 divide. So contravariant component of the metric tensor. This is the 1 divide on covariant component. It means that J0, 0, this is 1, so we have only 1, so we put here 1. Multiply on D on CT, because the first, the 0 coordinate, this is CT. C, this is speed of light. From, and J11, this is minus A square, the function of T, 1 minus K R square. Okay. So, and here we only need to know differential how to find derivative. So it will be here 2. We will have, of course, c. We will have 1 minus k r squared, because this this term doesn't depend on the time. And so the derivative of a square, we will have 2a point. And here I will clarify that if I have a point above of some letter, it means that this is derivative by time. Okay. So finally we have for this gamma 0, 1, 1, we have, so you can see that it's very simple. A point divide on C, 1 divide K R squared. So first one. What I will also need, this is...
possibly here must be minus, or not?
Yes, of course. Yeah, thank you. Should be minus. Minus here. Yes, minus here, and finally we will have plus. Yeah. In any case, so I found, yes, I lost the minus in one place, but the result is the same. Yeah, because here also we have minus. Thank you. So now we also will need to calculate the time component gamma 0, 2, 2. So, and again, look on this formula. We understand that it will be 1.5. Is minus, remember, and G220 divide on sorry. You know, I can, in principle, also to continue here, and for such a kind of metric, they can take out that the contravariant component of the metric tensor we express through the unit tensor. This I can write this also like this. Okay, this is the same. So in this case, I can write that here it will be G22. Oh no, sorry. G00. So, and we need to put here minus 1 divided on 2. Again, the derivative. So we put here J00, it's again unity. So very simple. D by C dt. And J22, this is what? This is this one. Okay. Minus R square, R square. So only A depend on the time. So finally we have R squared divide on C, A point. The same way we find gamma 3,3. So, and it will be minus 1.5, J330 divide. You know, I consider all these components because it's it will need us for 0 component. Mention equation J00. So minus So here we have we will have again unity d by c dt, and G33, this is okay, minus r square sinus square theta. So, and we have finally r square divided on c, a point sinus square theta. So also I will not prove it, it can be seen immediately that gamma 0, 0, 0 equal gamma 0, 0 alpha and equal 0. I also to be in time finally, so, and this is your also home task jointly. So please prove that 0 alpha alpha, so it means gamma 0 1 1, gamma 0 2 2 и так далее, and so on, equal 1 divided on c alpha point a point a alpha alpha. And we can immediately to generalize it for alpha beta. You repeat, but I just put like this. So it means that if we have a different where alpha doesn't equal beta, no. So alpha can be different, can be equal beta and not equal beta. So it means that when alpha, it's better to write like this, if alpha equal beta, the symbol, Christoffel symbol is not 0. But if alpha doesn't equal beta, so the gamma is 0. This is a point. You can prove it using the component. So now let's find the Richet tensor. Richet tensor, by definition, so which we found before in the lecture about Richet tensor, I just write the expression which we proved. RKM, so it is gamma. So in gamma take this Km, the first gamma, and after this we need to put L and to put L again. Here the comma is a derivative. So if I write like this, it means d by dxl, okay? Minus gamma, and now gamma take one index k here, and m we put after comma, and here we need to write these indexes plus, and the combination of two gamma. So this is km, one of the gamma take this k and m. After this we need to put the summation index n here and then here, and other summation index minus again combination gamma. And now the indexes are distributed between two gamma, so one index here, the second here. And after this, we need to put the summation index n, since it's below here, and L here. Again, we remember that Christoffel symbol is symmetrical relative to permutation of the lower indexes, so it doesn't matter NM or MN like this. So this is expression for the tensor, for the Ricci tensor. Ricci tensor, see lecture about Ricci tensor. And now we need to obtain the zero component of the Ricci tensor. So this is covariant component, but after this we can obtain quickly the mixed component. So we just need to put instead of I will. So okay. So I put here gamma 0 0 L L minus gamma 0 L L 0 plus gamma N L L gamma 0 0 N minus gamma N 0 L gamma N 0 L. So I had the business situation that we need to consider for all L to make the summation and all N now with the combination. And it's better to do like this. Let's consider what it will be, the term which correspond to the case L equal 0. So if I will put L equal 0, this term will be I will write even 0 minus gamma 0 0 0 plus gamma n 0 0 gamma 0 0 n minus gamma n 0 0 gamma n 0 0. So this of course disappear, and this also disappear because it's the same, so it will be 0. So we will have only situation when L, for example, equal alpha, so the space components. In this case, we have gamma gamma 0 0 alpha alpha minus gamma 0 alpha alpha 0 plus gamma n alpha alpha gamma 0 0 n minus gamma n 0 alpha gamma 0 alpha n. Okay, so since, and you will show you at home, we have the 0 component, this component of Christoffel symbol 0, this will disappear, it will be equal 0. The second one, no. We need to look at this. So let's continue. So here we will have minus gamma 0 alpha alpha 0, and we need to put instead of n, we need to put 0 1 2 3. So we will write like this: gamma n, oh sorry, instead to put n we put 0, alpha alpha gamma 0 0 0, and gamma is gamma 0 0 alpha gamma 0 0 n. So I put here n equals 0. Okay,
right,
right?
but in second
not
term
right.
you,
Okay, yeah.
you change n to 0, but in third term not.
Yeah, I can see that something wrong. Yeah, yes. Yes, yes, right.
No, possibly we just can yes, change this n to 0 and
okay, here something, yeah. Gamma 0 alpha 0. Now it's right. Yes. So and I will put also the summand. Now I will put n equal beta. So it's a space part. will be gamma beta alpha alpha, gamma 0 0 beta. Can you see what I'm writing? Because I try to now to write very compact, because it's much more convenient to have. Do you see everything? Yeah. Okay, so beta 0 alpha, gamma 0 alpha beta. So this I put here. N equal beta. And now we will look equal. So we see that this equals 0, again, due to the fact that gamma 0 0 0 equals 0, which is good for us. This is also will be 0, again, due to this fact. So, and also this will be 0. So finally we have that we even can write on the opposite page that R0 0 equal minus gamma 0 alpha alpha derivative 0 and minus gamma beta 0 alpha gamma 0 alpha beta, right? Yes. So this is what we have. And now we are ready to put exactly the expression for Christoffel symbols. Okay, so equal minus we have gamma this one, which we exactly need to show at home, that is like this. So okay, I will write here the gamma alpha right here, gamma alpha beta equal equal on C, okay, on the right hand C, A punta A delta beta alpha. Okay, so I can put it here. So now it will be 1 divided on C d by dt, and we need to put this one. So since also C, it will be 1 divided on C squared, A point divided on A delta alpha alpha. Okay, minus and here 1 divided on C squared, because it's, you know, this looks the same. So, and here we need to put A point divided on 8 square delta beta alpha delta alpha beta, like this. Okay, so equal here since we have delta delta, so here this is summation by alpha and by beta. So, and if this is this delta delta equals 3, because we need to consider the sum, and for alpha equal 1, for alpha equal 2, and for alpha equals 3. And all time we have a unity. So delta alpha alpha equal 1 plus 1 plus 1 equals 3. Okay. So we will have minus 3 divided on c square. And we need to take a derivative. So it will be a2 point multiply on a minus a point square divide on a square. About this one, so we will also have 3 because because we need to, when we have delta alpha beta and delta alpha beta, so it's understandable that it will be not 0 when alpha equal beta, okay? And this again will be 1 plus 1 plus 1 because 1 multiplying 1 divided equal 1. So minus 3 divided on c square, a square. And finally, what is beautiful is that 1 point disappear. So we have minus 3 divided on c square, a 2 point divided on a. Again, when I use 2 point, it means that this is d2 by dt twice, okay? So, so we obtain that r00 equal minus 3c square. I can write here like this. d by dt twice. Yes. So, and we're ready to no, we need to find the mixed component. So, so if you have a covariant component mk, for example, yes, or rich tensor, and you want to obtain the mixed component, we need to apply a metric tensor. So when we have r ik, what we exactly need in Einstein equation, this form which we wrote. So since we need, as we know, this one, exactly this one, okay, r00. Let's see what we will have here. R00 equal, just put here 0m r m0. So, and it's understandable that it will survive only 0 component of the metric tensor, which is not 0, and it will be 0 0 r 0 0. So since metric tensor component of the metric tensor 0 component equal unity, so we will have this case like r0 because this is unity. So, and it means that it will be this one. And finally, we obtain the 0 component, or this time component of the solution of Einstein equation for Friedman, Lemaitre, Robertson, Walker metric, which we can write. So on the left part, and I want to leave on the left part only a point, divide on 8. And on the right side, I will put this, okay, not to make a mistake. So I remember this is now 4, this is 4, should be not 8. Look here, this one. Oops. 4 P G C 4 epsilon plus 3P. Or, which will be much more beautiful, a point divide on 2 point divide on a equal 4 P G divided on is minus 3C square epsilon plus 3P. So, ta-da! Not incredible complicated, yes. So this is one of the equation of Friedmann-Lemaitre. We will play a little bit later and we will write it in much more comfortable way. But yeah, this is one of the equation of Friedmann-Lemaitre equation, the first one. It's called also acceleration equation. And look, we control everything because we understand why we have A with a 2 point, because this should be acceleration. Because, you know, when we also consider some the equation of motion, classical mechanics, we also have the second derivative. We understand why we have, and this is again the production of the Ricci tensor. Exactly, so we understand why it's like this. From the right side, we understand, we remember why we have a 4P J because it comes to us from Poisson equation. We understand why we have a C square because it's a relativistic case. So, and we also understand why here appears V, because it's come to us from this place. Okay, so here we obtain this 3, and this 3 exactly is related with the dimension of our space. So our space is has this 3 dimension, and this is exactly why we have here this 3. So epsilon, this is energy density, P, this is pressure. So this is the part which is responsible for the matter, which distributed in the universe. And later we'll consider which the equation of state we need to apply, considering to the fact which matter we need to put in our universe to correspond which component the universe has. Okay, so, and you will, for the home task, it's not all, so because you need to have the second equation. What is beautiful, that we, as a solution of Einstein equation for the Friedmann-Robertson, for the Friedmann-Lemaitre-Robertson electrometric, we will have only 2 equations, because the component R alpha, it will be survive only component of the Ricci tensor with the same indexes. So, sorry, yeah, of course it will be like this, it's already understandable, but okay, I will write like this. So R11 equal R22 equal R33. So they will be the same. In principle, and I will not ask you to, to repeat it for each component, but to write it in general cases I showed you, for example, for the time component. And it's understandable why, because, okay, we applied the cosmological principle. So we already put the symmetry in our system, that the space and distribution is homogeneous and isotropical. So, and of course, as a result, and you can prove it, you really can calculate and to see that it's like this. Immediately we understand that if we will not use cosmological principle, but we would like to consider much more complicated universe, God knows, maybe it's really much more complicated. So the number of equations will increase by definition. As a home task, I ask you, and as usual, you send me in PDF, it's better, your task, which you will solve, and I will take into account. You need to find the space component of for example, I will ask you to find R11. So this it will be a home task for the metric Friedman limit metric. Okay. So for this you need to find, and I will write the final expression because it's better to have it. For this you need to find. I just look. Okay, we need to find to obtain this. You need to find gamma 330, gamma 331, gamma 332, and in principle, yes, you also need to prove that gamma 000 equal gamma 222 equal gamma 333 and equal 0. You also need to prove that, and it will be convenient, maybe it's not so important. Yes, as I showed that gamma, or just find it, gamma 111, you also need to find, for example, as an answer I can write, which should equal kr divide 1 minus kr square. Okay, just for orientation that you are doing something right. Gamma 221, and it should be minus r1 divide kr square. Gamma 331, you need to find also gamma 332. For the space component, it's much more, it's a little complicated business, but and in principle, to find this, you can find the general expression also as a whole task. For example, which the general expression as I found before for this case, no, for this case. So just to see that it will be much more simple. For example, for when all components equal, this is 1 divided on 2, jk k k divide on jkk gkk. So what you also will need, so in principle, all symbol Christoffel, you need to find what you will need. Now I will not continue because so, and I will write the final expression for the space, for the let's try to find it. So final expression for R11 you need to obtain like this. Should be a point square divide on c square 1 minus k r square plus 2k divide 1 minus k r square minus 2 divide r square. No. Oh no, I'm not right. Sorry, kill it. Sorry, it should be this one, A, and this is right. Yeah, because it should be with acceleration. Plus 2A point square plus 2KC square divide on c square minus 1 minus k r square. So you need to finally, and you need to find much more Christoffel symbols, but you will see. So this is final expression. If you will not succeed, but even if you will not succeed, in any case, send me, for example, how you calculated that calculation of Christoffel symbols, that I will see that you tried. It's possible that you will not succeed because maybe it will be long or you will make some mistake. So if who will succeed, of course, we will obtain the higher the number of the mark for this home task. This is home task. It's understandable. And by the way, you can see here, because in the equation Friedmann-Lemaitre, this one, we don't have any information about the sign of the space curvature. But in this equation, as you know, we didn't write yet equation, but in this component, you will see that this curvature, the sign of the curvature, is already present. So, which is important. The second equation will keep the information about dynamics, which is related to the curvature of the space. Home task is, do you understand what to do? Everything is understandable. You can ask question.
Yes.
And yes, time. Okay, just a second. Yes, I give you for this 1 week up to next Friday as usually. Okay, question?
Can we use
Task. What we have and what we will found it, please. You understand me?
No, sorry. Please repeat.
Repeat, please. What you have, what you have, and what will found, and the construction.
The construction of what?
I'm sorry. Что мы имеем и что нам нужно найти? Вы могли бы сказать четко? Вот мы имеем это и нам найти. Вы очень сказали так по полочкам, но как-то не так конструктивно. Пожалуйста, повторите еще раз.
So you have this formula, okay?
Так.
Reach it answer.
Так,
You will need to obtain, as I obtained for the zero component, you need to obtain this R with the indexes. This one, 1, 1, and the answer here. For the Friedmann, from the Friedmann, Lemaitre, Robertson, Walker metric. So it means that you need to use this metric with all this description of this metric to obtain correspondingly, since in this formula for each answer you need to calculate Christoffel symbols. You need to obtain the first Christoffel symbols, and after this the corresponding component of the reached answer. So you need to obtain this expression to show me that your procedure, to show me all your calculation, and finally to prove that R1, 1 equal what you can see on the right side. So I explained understandable.
Thank you so much. Okay,
last question. Can we use some numerical methodics to find it or not?
Analytical you can't use, but
I don't know how.
What do you mean?
No, something like Wolfram.
You can use Wolfram Mathematica, but write with the hand finally. For example, you can say Wolfram Mathematica, please find me this derivative. Okay, if you are lazy to find it. In Wolfram Mathematica, I don't know that Wolfram Mathematica has.
So I'm about writing the cycle, which will give me all Aristotle symbols.
Okay, you can do it. In this case, you also will send me your program of Wolfram Mathematica.
Oh, okay.
So if you will write this procedure, yeah, in principle, yes, you can do like this. Or, for example, if somebody would like to use Wolfram Mathematica for some intermediate, calculations, in any case, who said it? Alexander or Denis?
No. That's me.
Simeon. In any case, you need to write also with the hand what you obtained. Okay, so Wolfram Mathematica, and you said, look in Wolfram Mathematica, or in PDF, you write the final result. In any case, for the reached answer, because you will. I'm not sure that you can write simply in Wolfram expression for the reached answer. For the Christoffel symbols, maybe. The principle, it can be. I know that my colleague, my friend, he wrote the program, spent some time to calculate Riemann tensor, Ricci tensor for some metric and for general metric and symbol Christoffel. But it's not so simple. But try, yeah. If you will write the program in Wolfram, send me the program in Wolfram, this final, and I will see that you succeed of this, or some part of the program, and after this you can write and obtain it by hand, as I like to say. It's understandable.
Yes, understandable. I will try to do it.
Yeah, it's interesting, yes. What is important to find the expression. So do you have some question? Okay, so this we will meet tomorrow, because tomorrow we have a lecture due to the schedule university. So please don't forget that tomorrow we have a lecture. Okay, so right, yes, cosmology, and which time? The same time today, as I can see. Right? Do you know about this?
Yeah, we know.
Okay. So, and tomorrow we will. So this task for you for up to the Friday, and tomorrow we will start to work with cosmological equation. I also will speak about lambda constant, and and to work already with cosmology to clarify which matter we need to take into account and how it's to understand the dynamics. So let's see you. Oh, it's already past 10 minutes. Yes, sorry. So see you tomorrow. Wait, don't move. I need to make a screenshot of what is important, not go out quickly from. Okay. So good day, everybody, and see you tomorrow.
Yes, thanks for collection. See you tomorrow.
Bye.